Picture this. It's 1928. A young, super shy physicist gets up in front of all the world's greatest scientific minds, and he presents a theory so strange, so completely nonsensical, that it literally drove them to despair. This is the story of that theory, an idea that started with a search for beauty and ended up discovering a hidden shadow universe. And to really get a feel for how badly this went over, just look at this quote. This isn't from some random critic. This is Werner Heisenberg, one of the founding fathers of quantum mechanics. What he felt wasn't just disagreement. It was like a deep, intellectual sadness.
And yeah, Heisenberg was definitely not alone. The story goes that after the lecture, the famously harsh Wolfgang Pauli just threw his hands up and announced he was quitting physics to go write a utopian novel. A novel. That's how much of a disaster they thought this new theory was.
So what on earth did this guy say? What idea was so horrifying that it threatened to just shatter the foundations of quantum mechanics? Well, to understand that, we have to go back and look at the massive problem he was trying to solve in the first place. You see, in the early 20th century, physics was kind of a house divided against itself. It was ruled by these two gigantic, incredible theories, but were also, well, completely incompatible. It was a cosmic clash that someone had to figure out how to solve. So on one side, you had Einstein's relativity, the theory of the super fast and the super big. It's where we get E equals mc squared. And on the other side, you have quantum mechanics, the super weird probabilistic theory of the incredibly small. The huge glaring problem? They just didn't play well together at all. Schrödinger's famous equation for quantum mechanics just fell apart when you tried to use it for particles moving close to the speed of light. The weird thing is, the conflict was hiding in plain sight, right inside Einstein's own work. If you look at the full version of his famous equation, you see this little plus or minus sign. It meant the math allowed for a negative energy solution. And for years, physicists just ignored it. I mean, negative energy? It sounded like nonsense. How could something have less than zero energy? So they just treated it like a mathematical typo and moved on.
But you can only ignore a problem for so long. The race was on to find a single, beautiful equation that could finally unite these two worlds. And this is where our guy, our protagonist, finally steps onto the scene.
Now, the first real crack at this was something called the Klein-Gorn equation. And it kind of worked. It merged the two theories. But it was ugly. The math was clunky, especially in how it handled time. And that clumsiness created a huge mess. It led to some totally absurd results, like negative probabilities, the chance of something happening being less than zero. To a physicist, that's a complete deal breaker. And this is where Paul Dirac, that strange young man we started with, comes in. See, Dirac operated on a totally different wavelength. For him, the real test of a theory wasn't just whether it fit the data, it was whether the math was beautiful. He genuinely believed that if an equation was ugly, it just couldn't be right. So Dirac's whole game plan was different. He insisted from the get-go that his equation had to be mathematically elegant, first order in time, to avoid that whole mess from before. But when he tried to build it, he hit a brick wall. The math just didn't work with regular numbers. And this is where he has this absolute stroke of genius. He thought, okay, if regular numbers don't work, why not use something else entirely? He decided to use matrices, these grids of numbers that follow their own weird set of rules. And that one radical move to use these strange mathematical objects didn't just fix his problem. Oh no, it cracked open a secret about the universe that absolutely no one saw coming. And the result was this, what he had been searching for, a new equation that described this incredibly deep pattern in nature. And it was breathtakingly simple and symmetrical. It was a thing of beauty. In Dirac's mind, it had to be the truth. And man, was it a success. Not only did it work perfectly with relativity, but it also accidentally predicted this known property of electrons called spin. It solved a huge mystery of the time, not because he was trying to, but simply as a side effect of making the equation beautiful. How wild is that? Okay, so this brings us right back to where we started. If this equation was so brilliant, so successful, why the despair? Why did Heisenberg call it the saddest chapter in modern physics? Because for all its elegance, for all its success, that same old ghost was still rattling around inside, the negative energy problem. His beautiful equations stubbornly, unavoidably predicted that an electron could just keep falling and falling forever into an infinite abyss of negative energy. The problem he tried to solve was back, and it seemed even worse than before. So for 3 years, Dirac is defending this beautiful equation from what looked like a fatal flaw. And then, in 1931, he came up with an explanation so wild, so out there, it sounded like something straight out of science fiction. He said the negative energy solutions weren't a bug, they were a feature. They were a prediction of a brand new particle, an anti-electron, a perfect mirror image of the electron, but with a positive charge. And this absolutely wild idea, an idea he literally invented just to save his beautiful equation, was about to completely rewrite our understanding of reality, and it would lead us to one of the biggest mysteries in all of science. And you know what's crazy? He was proven right. And not in like a decade, almost immediately. Just 1 year later, a physicist named Carl Anderson was looking at cosmic rays and saw something weird, a particle that had the exact same mass as an electron, but curved the wrong way in a magnetic field. He had, completely by accident, discovered Dirac's anti-electron, which he called the positron. The wild idea was real. Now, today, our understanding is even more elegant. Thanks to physicists like Richard Feynman, we don't have to worry about some infinite abyss of negative energy anymore. The modern view is just beautiful. A negative energy solution is just the math's way of describing an antiparticle moving backward in time. It all just clicks into place. But here's the thing about physics. You solve one giant puzzle, and you often find an even bigger, scarier one hiding right behind it. See, according to our theories, the Big Bang should have created matter and antimatter in perfectly equal amounts. And if that had happened, they would have found each other and, poof, annihilated, leaving behind a universe with nothing in it but light. But, I mean, look around. We're here. The chairs we're sitting on, the planet we're on, it's all matter. For that to happen, there had to be a tiny, tiny imbalance right at the start. For every 1 billion pairs of matter and antimatter particles that wiped each other out, just one extra particle of matter had to survive. Just one in a billion. And that leaves us with maybe the biggest question there is. Everything we see, every star, every galaxy, you and me, we're all just the leftover cosmic rounding error. And it all started with one man's obsession with a beautiful equation. So the ultimate mystery is this: why are we here at all? Why did matter win?